These are the chapter 24. Ooh, I can move in and out here. Chapter 24 homework solutions for AP Physics 2. Okay, that was not what I want to do. Anyhow, I want to go through these. And we didn't have much time in class, really any time in class. I did post a couple sample problems outside of class. And the conceptual questions we went over related to a few of these. So these are problems 5, 13, 25, 33, 44, 46, 47, and 57. So for problem 5, it says if you have 10 amp current in the upper wire, unknown current in the lower wire, both currents are going to the right. Point P is 2 centimeters from the lower wire and 1 centimeter from the upper wire. Find the amount of current in the bottom wire. If we go back to this formula, which is one of the ones that's both on your formula sheet, I think that is formula E19, and it's also in chapter 24. You can see that magnetic field strength is directly related with current, inversely related with distance. So if this point P is twice as far from the bottom wire as the top wire, the current in the bottom wire should be twice as big. So without any real in-depth calculation, I can find out that the current in the bottom wire will be 20 amps in order to get zero net field. So it's not that there would be zero net force if there was a charge there, but there's zero net field at that point. For problem 13, you're given basically a solenoid, radius of 30 centimeters, 1,000 turns, 1 Tesla in the center, find the current. So this is a formula in chapter 24 also. It deals with N is number of turns, L is length of the solenoid, so it's turns per length, and then those affect the amount of the amount of magnetic field strength. That's not a formula on your formula sheet, but I seem to remember that this is something that may end up popping up from time to time. Okay, at any rate, next one down here. So that just basically, that's a lot of current, by the way. Like that would melt most wires, so I'm not sure if that's a realistic value. For problem 25, you're given a field strength and you're asked to find the radius of an electron and proton that are going through the Earth's magnetic field, which has this field strength approximately, if they're going certain speeds as they hit the atmosphere. So the mass of an electron on your formula sheet, charge an electron and a proton both is 1.6 times 10 to the negative 19th coulombs. You should know that by now from things we've done, but if not, that's also on your formula sheet. So I derived this in class. I basically said a centripetal force, or the magnetic force would act like a centripetal force because it is always acting perpendicular to the motion of the charge. And so we can solve for R is equal to mv over qb. And that radius, 0.114 meters for an electron, 10.4 meters for a proton. So proton has more mass, it's going slower, but overall that results in a larger radius. Problem 33, 34, 46, 47 deal with forces acting on things in a magnetic field. Problem 33 deals with a wire. It's got current going to the left of 1.5 amps. It says it's a 2-gram wire. So, and you're asked to figure out if that's going through a 10 centimeter area of or length of magnetic field, what's the amount of current? Big idea, balance forces. So I drew a free body diagram over here. Gravitational force would be down, magnetic force would be up. And in this particular case, got 1.5 amps to the left. So I'm going to use the Fabel formula for magnetic force on a wire. That gets me 0.01 force, or pardon me. In order to get that, I need to know the amount of gravitational force. So that's mg. 2 times 10 to the negative 3rd kilograms, 9 times 9.8 newtons per kilogram. So it gets me that force down. So therefore I need that force up, which is 0.0196. Sorry, that looks like 0.0146, but it's 0.0196. And that equals B times I times L. I know everything except B. So I'm going to get 0.131 Tesla, and that's going to be pointing out of the page. So I use the right-hand rule for current with my fingers pointing out of the page, the thumb is pointing to the left, and that would cause an upward force. For problem 4, it's asking for the amount of force on this circuit if it goes through a magnetic field over on this side here. With any force on the top part of the wire and the bottom part of the wire would cancel out since the currents are going different directions. A 15-volt power source, a 3 ohm resistor, so that's going to get me 5 amps of current using Ohm's law. And now if I have 5 amps of current going down in this region where I have the magnetic field going into the page, that lets me know that I'm going to have a force directed to the right. And I use here this FB equals B times I times L to get the amount of force, which is 0.025 newtons. Problem 46, another problem with balance forces. So we've got an electron coming in here in an electric field. It's going straight to the right. You want to, obviously that electron would be repelled from the bottom and attracted to the top, so there's an electric force up. Your goal is to have this electron go in a straight line, so therefore you need a magnetic force down. So the first thing is you got to realize there's balance forces. If it's an electron, we use the left-hand rule. And in order to get a magnetic force down, that means the magnetic field would be pointing into the page. The next thing I did, and you can do these in a little bit different order, I just like to get the idea of this up there first, is we want to find the electric field strength from the given info. So it told me the potential difference was 200 volts and this was 1 centimeter. Formula E6 on your formula sheet shows that a potential difference divided by distance is equal to the magnitude of electric field. So that comes down to 20,000 volts per meter. However, electric field is also equal to force over charge. And I think I did a kind of a mini proof or a derivation of a formula in class where I showed you that force over charge and volts over meters really end up being the same thing, which is a little surprising. At any rate, I can use this, which is formula E6, to get 20,000 volts per meter. I need to realize that also could equal 20,000 newtons per coulomb and would equal force per charge. So I can rearrange that to solve for the electric force is equal to electric field times charge. Well, the magnetic force is equal to charge times the speed that the charge is moving times the magnetic field strength that the charge is moving through. So since the magnitudes of these are going to be equal, I'll set them equal to each other. Notice even though it's lowercase q and uppercase q, it's the same charge moving through the fields. So those cancel out, which is kind of interesting. And so the electric field strength equals the velocity times the magnetic field strength. So the magnetic field strength would be 0.002 Tesla, and that would be into the page in this situation. Last two problems, problem 47 and 57. This is very similar to one that we had as a conceptual question, except here we're actually putting some numbers in. So you've got a wire, current going upward, magnetic field coming out of the page. It's attached to 2 springs. That current going upward would cause a magnetic force to the right, so the springs have to pull back to the left. Again, I drew a free body diagram over here showing that 2 spring forces would equal 1 magnetic force. Force on a spring via Hooke's law formula here, which is K times delta X would equal the spring force, and B times I times L is equal to the magnetic force. So since those two are equal, I set them equal down here mathematically, and I get that the current is 2 amps. Current here, 240, problem 57 is another solenoid problem. This is a pretty straightforward problem. I go back to that formula I had. It tells you, and this is true, if you have something that's made of iron, nickel, or cobalt, those are ferromagnetic materials, and if you have a magnetic field inside the solenoid wrapping the solenoid coils are around something that's ferromagnetic, it greatly amplifies the magnetic field strength. In this case, it said by 100 times. I'll demonstrate that in class when we get to something with chapter 25. So here all you ended up doing is using that formula, multiply it by 100 since it told you the properties were magnified by 100. And I get that the field strength would be 1.01 Tesla. Your book might have rounded to 1.0 Tesla. So hopefully those make sense. Please look over those. I know We're going really quick through the magnetic part here, but I do think it's something you can understand. I think you're really thinking about a new type of force, and that force exists on charges that are moving through a magnetic field. So magnetic force is caused by an interaction of two magnetic fields. Oftentimes in this chapter, it's a permanent magnetic field and a temporary magnetic field caused by a charge moving. Could be two temporary magnetic fields or two permanent magnetic fields could also cause a magnetic force. Thanks, and hopefully that makes sense.